Hey everybody, let's talk about shear force and bending moment diagrams. So previously what we would do is, say we had this beam supported by a roller and a pin, subject to a discrete load here and a distributed load here. We would do something like solve for the internal forces and moments at this point right here. Right, so that's what we did previously. What we want now is the internal forces and moments at every point along the beam as a function. So this beam is along axis over here, x-axis. So let's say we want the shear force as a function of x, whatever that looks like. We want the bending moment as a function of x, whatever that looks like, for every point along the entire axis. Okay, so how do we do that? Let's start with the free body diagram of the entire thing so that we can solve for the reactions at these two supports. So let's use this example. So if I have coordinates, say, right over here, x and y, I'll decompose the pin support at B into x and y components. And then I have the roller at A. And then we have this discrete load here. And then the distributed load, which we can represent as a single discrete force. And the magnitude of that force is the area of the shape. So 40 times 2, 80. And then the position of that force is at the centroid of the shape. So it's a rectangle, so it's just in the middle of the rectangle. So just like halfway. Okay, so here's our free body diagram. Now we can solve. Okay, so in the x direction we got, let's see, what do we have here? Bx. That's it. Y direction, I'll just call this AY. By minus 80 plus 60. Okay, let's sum torque about somewhere clever. How about over here? About point B. Okay, so the lever arm to here is 1 meter. So 1 meter times 80 kilonewtons. The lever arm to AY is 2 meters, and that's going in the negative z direction, so minus 2 meters. AY, the lever arm to this is 2 meters plus 2 meters times 60. Okay, let me point out the unknowns. Here, 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 here. Okay, so what do you want to solve for? Bx is 0. AY, there's only one unknown here. Right? Okay, so then let's see. We got 80, 120, so that's 200 equals 2AY. Okay, so AY is 100. And then substitute that value here. So then BY is, let's see, that's 20 minus AY. So BY is negative 80 and BX was 0. Okay, so we have all three reactions at those supports. Now, what we want to do is cut through this free body diagram at some point, some arbitrary point. So and we don't want to use this representation anymore. We're done with this. This was only to solve for these three reactions. That was the point of using this. So now that we're done with it, we're not going to use it. We're back to the original. Okay, like this. And what were our values? Bx is 0, by is negative 80. So I drew my arrow going upwards, but the value is actually negative, so it's actually going this way. Okay, and then AY was 100 over here. And then what else? Oh, and then the 60 kilonewtons over here, and this was 40. Okay, so here's what we do. If we cut a section somewhere between here and here, no matter where we cut it, at some arbitrary x between 0 and 2 meters. So this is x between 0 and 2 meters. No matter where we cut it between 0 and 2 meters, let's see if you agree. The free body diagrams will look like this. Okay. There. Right? It'll always look like this. I mean, this part might be shorter or longer, this part might be shorter or longer, but generally, the free body diagrams will look like this. And then there's all the internal forces and moments over here. Right, M, P, V, the shear, axial force, bending moment. Right, so anywhere we cut it between 0 and 2 meters, the left section will look like this, the right section will look like this. Which section would you like to analyze? I feel like this one is a little less complicated, so I'm just going to get rid of this one. We don't need to analyze both, right? You're going to get the same answer either way, so just pick the easier one. Okay, now here's the thing. What if we cut the section somewhere over here between 2 and 4 meters? So if you cut the beam between 2 and 4 meters, let's see if you agree that it'll always look something like this. Right? If we cut it somewhere between 2 and 4 meters, the left section will always, then all the internal forces and moments. Right? The left section will always look like this. From here to here, the length will change. And the right section will always look like this. And then, given the choice, I feel like the right section is much simpler. Okay, so I'm going to get rid of this, and then I'm going to save this for later. This is the right section when we cut x between 2 and 4 meters. This is the section when we cut it between 0 and 2 meters. Okay, so now how do we analyze this? Now that we cut the section, now it's okay to represent this distributed load as a single discrete force. Now what is the magnitude of this? It's the area of this rectangle. What's the area of the rectangle? How far is it from here to here? X, right? I cut it at some arbitrary X. And then here to here is 40. So this is 40X. Right? It just depends where we cut it. And where is that? Here to here is 1/2 of X. Right? Here to here is 1/2 X. Okay. All right, so there we go. Now we can write equations to solve for this. Okay, so x direction, we got this. That's it. Okay, y direction, 100 minus 40x minus v. Okay, sum torque about anywhere we want. If I sum torque about this side, then there's torque from this force and this couple. If I sum torque about this side, then there's torque from this force, and this couple. I feel like that choice is more clever because I don't need to deal with this variable. One less unknown. Okay, so I'm going to sum torque about the right side, the end. Okay, so that's going to be 40x times 1/2 x, 1/2 x times 40x. And then from this would be minus, here to here is x, and then 100. Okay, and then there's also the couple here, and my coordinates were like this. So z is this way, so that's positive z, so plus. Okay, and then let me point out the unknowns here, here, here for variable x. So let's solve. So P is 0. So the axial force is 0. The shear force as a function is 100 minus 40x. Then the bending moment, this equation right here, as a function is 100x minus 20x squared. Okay, so this particular question was just asking for, let's see, I'm just going to write this as a function, even though it's... Okay, look, we have the axial force, shear, and bending moment as functions, but this is only valid for x between 0 and 2. Okay, let's solve for the rest of it between 2 and 4. So we have this free body diagram. Let me draw the arrows bigger. Okay, so we got axial force, shear, bending moment. Okay, and how far is this? If we cut, let me go back to the original picture. Right, here's the original picture. Okay, so if we cut it somewhere over here, like that, between 2 and 4. So this, right, then how far is this? This has got to be 4 minus x, right? Because here to here is 4. Let me look at the picture. Yes, okay. Right, so if here to here is x, here to here has got to be 4 minus x. Okay, so now let's solve for these unknowns. Okay, so x direction. We got minus p, then that's it. Y direction, we have v plus 60. That's it. Right, let's sum torque about anywhere we want. So we can sum torque about this side or this side. If I sum torque about here, there's no torque from this unknown, so I feel like that's more clever if I sum torque about the left. Okay, so then here to here is 4 minus x times 60. That's going in the positive z direction. And then this is going in the negative z direction. And here we go. So here, P, 0, here, V, negative 60, M is, I'll just copy that down, so, or you can multiply it through 240 minus 60x, or you could just leave it like that, same thing, right? Okay, and this is true for x between 2 and 4 meters. So it'll almost fit on the screen, right? So now look, we have the behavior of axial force, shear, and bending moment over the entire beam. And just for visual purposes, I'm just going to copy this so we can see it all on the same screen. Okay. All right, so for the axial force, it's just 0 everywhere, so maybe I don't need to graph that. For shear, as a function of x, see, so between 0 and 2, it looks like this. So the y-intercept is 100, and the slope is negative 40. At x equal 2, it's 100 minus 80, so kind of looks like that. And then for x between 2 and 4, it's negative 60. So it just kind of suddenly changes like this. And there we go. So that's what the shear looks like. And this was, how much was that? Negative 60 over here. This was 20. And this was 100 kilonewtons, right? Okay, and then how about the bending moment? So from 0 to 2, say, so 100x minus, so at x equal to 0, it's at 0. At x equal to 2, it is 200 minus 2, so 80, so 120. And then see how it's like this. It's a parabola, but see that's a negative, so it's upside down parabola. So it looks kind of like this. Okay, and then between 2 and 4, at x equal to 2, it's 120, so it's right here again. And then the slope is like this. So it looks like going linearly, and at x equal to 4, it's 0. Okay, so it looks like this. There you go. And I'm not saying that you need to know how to graph things by just looking at it. You can just, graph it on your calculator on a computer. But it is important to visualize what's happening. So right, if you look at the shear, this gives you as an engineer important information. Like, okay, the shear is a maximum over here. Then there's a sudden change here at x equal to 2 meters, and then it's constant over here. What about the bending moment? Where is the maximum? The maximum is right here. And then we can even get the value, right? It was, what was it, 120? Okay, so that's all important information that informs decisions you make as an engineer for designs. Okay, so give these a try. Be very careful when you cut your section. Make sure to cut the original value, not this representation over here. Right? Be careful not to do that. Okay, so let me know if you have questions in the forum, and I'll see you in the next video.